dear students, glad to meet you again in this session 2.12. In this session from chapter 2, Structure of Atom in grade 11, we are going to discuss the electronic configuration of first 20 atoms in part 1. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 1, we have discussed the discovery of subatomic particles. In session 2.2, we have discussed J.J. Thomson and Rutherford atomic model and its drawbacks. In session 2.3, we have discussed dual nature of electromagnetic radiation. In session 2.4, we have discussed atomic spectra. In session 2.5, we have discussed Bohr's atomic model. In session 2.6, we have seen two developments towards quantum mechanical model of atom. In session 2.7, we have discussed quantum mechanical model of atom. In session 2.8, we have discussed orbital and quantum numbers. In session 2.9, we have discussed shapes of orbitals. In session 2.10, we have discussed energies of orbitals. In session 2.11, we have discussed filling up of orbital. Learning outcomes. Students, at the end of the session, you will be able to state electronic configuration of atoms, list and describe the notation of electronic configuration, and write the electronic configuration for the first 20 atoms in terms of scientific notation and orbital diagram. Now let's recall all the three rules that we have discussed in the previous sessions. According to Aufbau principle, in the ground state of the atoms, the orbitals are filled in the order of their increasing energies. To easily memorize this order of increasing energy, we have discussed diagonal rule of electron filling order. The next one is Pauli's exclusion principle. According to Pauli's exclusion principle, no two electrons in an atom can have the same set of all the four quantum numbers. And the third one is the Hund's rule of maximum multiplicity. According to this rule, pairing up of electrons takes place only when there is no empty orbital. In this session, based on these three rules, we are going to learn how to construct the electronic configuration of an atom. Electronic configuration of atoms. The distribution of electrons into various orbitals of an atom is called electronic configuration. Notations of electronic configuration. The electronic configuration of different atoms can be represented in two ways. What are they? They are scientific notation and orbital diagram. In the first notation, that is the scientific notation, the subshell is represented by the respective letter symbol. For example, to represent S suborbital or subshell, it is written by the letter small s. To represent p orbital, it is represented by its respective letter symbol, that is small p. To represent d orbital, it is represented by the letter small d. The number of electrons present in the subshell is depicted as the superscript. For example, how many electrons are there in s orbital? 2. On the whole, how many electrons will be there in the p orbital? 6, right? Because it has 3 suborbitals. P in the x direction, P in the y direction, and P in the z direction, right? So on the whole, how many electrons will be there? 6. So p orbital has 6 electrons. Coming to d orbital, it has how many subshells? 5. So 5 into 2, on the whole, how many electrons will be there in d orbital? 10. So to represent the number of electrons present in the subshell, it is depicted as the superscript. To represent the number of electrons present in s orbital, we have to write 2 in the superscript of small s. The subshells which is present in different shells like K, L, M and so on is represented by writing the principal quantum number before the respective subshell. For example, let us take the K shell. In the K shell, we have S suborbital, right? So we have to write small s over here. Then how many electrons, number of electrons present in S suborbital? 2. So we have to write 2 in the superscript of S. And this S orbital is present in the K shell, right? So what is the principal quantum number for K shell? N equal to 1. So we have to write 1 in front of the name of the suborbital. In scientific notation, to represent the s orbital in the K shell, we have to write 1s2, where 1 is the value of the principal quantum number, s is the name of the suborbital, and 2 is the number of electrons. Now coming to the second notation, orbital diagram. In the second notation, each orbital is represented by a box. The suborbitals present in the shell K, L, M, and so on is represented by writing the principal quantum number before the respective subshell. For example, to represent the s orbital in the K shell, we have to write 1s either at the top of the box or at the bottom of the box. And how many electrons are there in s orbital? 2, right? So the electrons present in the suborbital is represented by an upward arrow mark for positive spin and downward arrow mark for a negative spin. The advantage of the second notation over the first is that it represents all the 4 quantum numbers. Electronic configuration of atoms. Based on the rules of filling up of orbital, we are now going to learn how to write the electronic configuration of some elements. First, let us take hydrogen. The atomic number of hydrogen is 1. So, it has only 1 electron which goes in the orbital with lowest energy. So, it will be in the s suborbital, which is in the K shell. To represent the electronic configuration of hydrogen in scientific notation, since this electron is present in the s orbital in the K shell, what is the value of its principal quantum number? 1, right? So 1, yes. How many electrons are there? 1 electron. So 1, yes. In the superscript, we have to write what is the number of electron? 1, right? So we have to write 1, yes, 1. Now, to represent the electronic configuration of hydrogen by orbital diagram, to represent the orbital, first we have to draw a box. Since this electron is present in the s suborbital, which is in the K shell, we have to write 1s. We can write this 1s either at the top of the box or we can write it at the bottom of the box. How many electrons are there? Only 1 electron, right? Now, to represent the number of electrons present in this suborbital, it is represented by an upward arrow mark. Next is helium. Atomic number of helium is 2. So, how many electrons are there? 2 electrons are there, which is present in the K shell. And in the K shell, we have s suborbital alone, right? So, to represent the s suborbital, we have written s. Since this is the first shell, the principal quantum number is 1. So 1, yes. How many electrons are there? 2 electrons. So in the superscript, we have to write 2. 1s2. This is the electronic configuration of helium in scientific notation. To represent the electronic configuration of helium by orbital diagram, then we have to draw a box which represents the suborbital. These 2 electrons present in s orbital, right? And it is present in the K shell. So we have to write 1s. How many electrons are there? Here we have 2 electrons. So to represent these 2 electrons in the s suborbital, we have to draw an upward arrow mark which represents the first electron with a positive spin, and we have to draw a downward arrow mark which represents the second electron with negative spin. Now let us write the electronic configuration of lithium, beryllium, and boron. The numbers you could see in the top right corner is the atomic number of the atom. For lithium, what is the atomic number? 3. For beryllium, we have 4. For boron, we have 5. These atomic number represents the number of electrons present in the respective atom. Now let us use the diagonal rule to write the increasing order of energies. We know that we have to start from the top right corner and moves towards the bottom left corner. So which is the lowest energy level? 1s. So 1s we have written. Then after 1s, again we have to go to the second diagonal line. 2s, right? So we have to write 2s here. We know that s orbital can accommodate how many electrons? What is the maximum number of electrons that can accommodate in s orbital? 2, right? So 2 we have to write. In the second shell, in the s orbital, how many electrons it could accommodate? It could accommodate the maximum of 2 electrons. But we have only 3 electrons in lithium. Already we have written 2 in 1s orbital. What is the remaining? Remaining we have only 1. So 2s1. So the electronic configuration of lithium in terms of scientific notation is 1s2 and 2s1. Now we can write this electronic configuration in terms of orbital diagram. To represent the orbitals, first we have to draw box. How many electrons are there? 2 electrons. Out of these 2 electrons, one will have the positive spin and another will have the negative spin, right? Because according to Pauli's exclusion principle, no 2 electrons will have the same set of all the 4 quantum numbers. So we have to represent 1 electron with upward direction, which represents the positive spin, and 1 with the downward direction, which represents the negative spin. Now coming to 2s orbital. How many electrons we have? Only 1 electron, right? So we have to draw an upward arrow mark which represents the positive spin. So totally how many electrons are there? 3 electrons in lithium. So this is the electronic representation of lithium in terms of orbital diagram. Coming to beryllium, we have how many electrons? 4 electrons. So shall we start writing the electronic configuration? The first lower energy level is 1s. So 1s. Coming to the second diagonal line, the next higher energy level is 2s, right? So we have written 2s here. And very well we know that each suborbital can accommodate the maximum of 2 electrons, right? So 2 electrons in 1s orbital and the remaining 2 electrons will be there in the 2s orbital. So what is the electronic configuration of beryllium? 1s2, 2s2 in terms of scientific notation. Coming to orbital diagram for beryllium, we have to draw one box for 1s and another box for 2s. How many electrons are present in 1s? 2 electrons, right? So out of 4, we have to draw 2 electrons inside this 1s orbital, one in the upward direction and one in the downward direction. Coming to 2s orbital, we have remaining 2 electrons, right? Those 2 electrons will be in the opposite direction, right? So one in the upward direction, which represents the positive spin, and one in the downward direction, we have to draw the arrow mark to represent the negative spin. So totally how many electrons are there? 4 electrons. Now coming to boron. Boron has how many electrons? 5 electrons. Shall we start writing the electronic configuration in scientific notation? For that, let us use this diagonal rule. First one is 1, yes, because we have to move from the top right corner to the bottom left corner, right? 1s. Coming to the next diagonal line, we have 2s. So we have written 2s here. We know that this s orbital can accommodate only 2 electrons. So 1s, 2. Then for 2s also, it can accommodate how many electrons? 2 electrons. So 2s, 2. So totally 4 electrons we have written. Remaining 1 electron we have. So coming to the next third diagonal line, we have 2p, right? So we have to write 2p here and write the remaining 1 electron in the superscript of p. So totally 2 plus 2 plus 1 on the whole 5 electrons for boron. Now shall we write the orbital diagram for boron? For 1s, we have to draw one box. For 2s, we have to draw another box. P orbital has px, py and pz orbitals, right? So we need to draw 3 boxes, continuous box. Since we have only one electron, it will accommodate in the first box 2px, and we have to represent this electron with an upward arrow mark which represents the positive spin. The other two orbitals will be empty. So 1s2, 2s2 and 2p1. This is the orbital diagram for boron. Now let us write the electronic configuration of carbon 6, nitrogen atomic number 7 and oxygen atomic number 8. Now first let us write the electronic configuration of carbon atomic number 6. To write the electronic configuration in the increasing order of energies, let us use this diagonal rule. In the diagonal rule, we have to start from the top right corner and move slowly down towards the bottom left corner. So which is the lowest orbital? 1s. So we need to start with 1s. 1s, then coming to the second diagonal line, we have 2s. So we have to write 2s. And coming to the third diagonal line, we have 2p. So we have to write 2p over here. How many electrons are there? 6 electrons. And we know that each suborbitals can accommodate the maximum number of 2 electrons. So we need to write 2 in 1s orbital, 2 in 2s orbital, totally 4. Then the remaining is 2, right? Then we have to write 2 in the 2p orbital. Now let us see the orbital diagram for C6. For 1s orbital, we need to draw one box. For 2s orbital, we have to draw another box. For 2p orbitals, we know that we have 3 orbitals, right? So we have to draw 3 consecutive boxes. One for 2px, another for 2py, and the last one for 2pz. To represent 2 electrons in 1s orbital, we need to draw one upward arrow mark and one downward arrow mark, which represent opposite spins of electrons present in 1s orbital. To represent the 2 electrons present in 2s orbital, again we need to draw one upward arrow mark and a downward arrow mark, which represents opposite spins of electrons present in 2s. While filling the p orbitals, we need to remember the Hund's rule of maximum multiplicity, which tells us pairing up of electrons takes place only when there is no empty orbital. So these two remaining 2 electrons, which is in p orbital, it won't pair up in 2px. Instead, one electron will go to 2px orbital and another electron will go to 2py orbital. So this electron in 2px is represented by upward arrow mark, and this electron in 2py is represented by upward arrow mark. Both of these electrons will have positive spin in the respective suborbital. The 2pz orbital will be empty. So on the whole, 2 electrons in 1s plus 2 electrons in 2s, totally 4, plus 1 electron in 2px, 5 electron. Then the 6th electron will be in 2py. So on the whole, how much we have? We have 6 electrons. And this is the orbital diagram for carbon 6. Now let us write for nitrogen 7. As usual, to write the electronic configuration in terms of scientific notation, we need to use this diagonal rule. Starting from the top right corner, 1s. Then coming to the second diagonal line, we have 2s. Then coming to the third diagonal line, we have 2p. So we have to write 1s, 2s and 2p. We know that each suborbital can accommodate maximum of 2 electrons, right? So we have to write 1s2, then 2s2. 2 plus 2, 4. 4, we have 3 remaining electrons. So we have to write these 3 remaining electrons in the p orbital. Pairing up of electrons takes place only when there is no empty orbital. So here pairing of electrons won't take place. So we should not pair electrons in 2px or in 2py, right? So we have to write 1 electron in 2px, 1 electron in 2py, 2py and 1 electron in 2pz. To represent these electrons in the p orbitals, we need to draw upward arrow mark in 2px orbital, one upward arrow mark in 2py orbital, and one upward arrow mark in 2pz orbitals. All these electrons will have positive spin. If we check the number of electrons, we have 2 in 1s plus 2 in 2s, 2 plus 2, 4, plus 1 in 2px, 5, plus 1 in 2py, 6, plus 1 in 2pz, 7. So this is the orbital diagram for nitrogen. Coming to oxygen. To write the electronic configuration of oxygen, again we have to use this diagonal rule starting from the top right corner 1s, then coming to the next diagonal line 2s, then coming to the next diagonal line 2p. So we can stop up to 2p because we have only 8 electrons, right? So 2 in the 1s orbital and 2 in the 2s orbital, 2 plus 2, 4. So 8 minus 4 remaining, how much we have? 4 electrons. We know that p orbitals can accommodate, on the whole, it can accommodate 6 electrons. That is 2 in the 2px, 2 in the 2py, and 2 in the 2pz orbital, right? But only we have 4 remaining electrons. So we can write 2p4 over here. Now shall we write the orbital diagram for oxygen? So we need to draw one box for 1s orbital, one box for 2s orbital, and 3 consecutive boxes for 2p orbitals. How many electrons are there in 1s orbital? 2 electrons. So one upward arrow mark and one downward arrow mark. Coming to the next orbital, we have 2 electrons. So one upward arrow mark we need to draw and one downward arrow mark, which represents the opposite spins of electrons in an orbital. Now coming to 2p orbitals. These are called degenerate orbitals, right? Degenerate orbitals have same energy. The only difference is the orientation. The x direction, y direction, and z direction. Now, how many electrons we have? 4 electrons in 2p orbital. According to Hund's rule of maximum multiplicity, pairing up of electrons takes place only when there is no empty orbital. Out of these 4 electrons, which is present in 2p orbital, the first electron will occupy 2px suborbital. It won't get paired up. So initially, there won't be any pairing. First, 1 electron out of this 4 electron occupy 2px. The second electron will occupy 2py. And the third electron will occupy 2pz. Then there is no empty orbital now, right? Then only pairing up of electrons takes place and the 4th electron will pair up in 2px suborbital. The first 3 will occupy the px, py, and pz. Then only pairing will take place. So while writing the electrons in p orbitals, first you need to fill up 1 electron in each orbital. That is why I have given in black upward arrow mark. Then only pairing will take place. So to differentiate the upward and the downward direction, I have given separate colors. Upward in black color and downward arrow mark in pink color. Now let us see the electronic configuration of fluorine, atomic number 9. So it has 9 electrons. To write the electronic configuration in the increasing order of energy, we have to write 1s2, 2s2 because we know that s orbitals can accommodate a maximum of 2 electrons. So 2 plus 2, 4. Totally we have 9 over here. So 9 minus 4, remaining 5 electrons will be there. We can write this 5 electrons, the superscript of 2p, because we know that p orbitals can accommodate a maximum of 6 electrons since it contains 2px, 2py, and 2pz. Coming to orbital diagram, we know that we have to draw rectangular boxes for each and every suborbital. So we have drawn box over here. For the number of electrons, we have drawn one upward and downward arrow mark for 1s and 2s, which represents the opposite spins of electrons present in 1s and 2s. Coming to 2p, it follows Hund's rule of maximum multiplicity. So out of this 5, first three electrons will occupy 2px, 2py, and 2pz respectively. Once it got filled up, then the fourth electron will pair with the electron present in 2px, and the fifth electron will pair with the electron in 2py. Neon has the atomic number 10. So to write the electronic configuration, we have to write 1s2, 2s2, 2 plus 2, 4. We have 10 over here. So 10 minus 4, remaining 6. We can write all the 6 electrons in 2p. To draw the orbital diagram for neon, we have to draw boxes for each and every suborbital. And each and every suborbital can accommodate a maximum of 2 electrons, right? So for 1s and 2s, we have to draw one upward and downward arrow mark, which represents the number of electrons having opposite spin. Coming to 2p orbital, according to Hund's rule of maximum multiplicity, the first three electrons will occupy 2px, 2py, and 2pz respectively. Then only the fourth electron will pair up with the electron in 2px, the fifth electron will pair up with the electron in 2py, and the sixth electron will pair up with the electron in 2pz. When you look at the electronic configuration, the orbital diagram for neon, here all the electrons are completely filled, right? The electrons in the completely filled shells are known as core electrons. So far, we have completed the electronic configuration of the first 10 atoms. Now, for the next 8 elements, that is from sodium to argon, it follows exactly the same pattern as the elements from lithium to neon. The difference is that the 3s and the 3p orbitals are getting filled now. Now let us see the electronic configuration of sodium, atomic number 11. So it has 11 electrons. So according to APA principle, we have to write 1s2, 2s2, 2p6. Up to this, we have 10 electrons. Totally, we have 11 in sodium. So 11 minus 10, 1 is remaining. That remaining 1 electron will occupy the 3s orbital. When you look at the configuration of sodium, we could see the neon configuration, right? Till 1s2, 2s2, and 2p6. So instead of writing 1s2, 2s2, and 2p6, we can write the symbol of neon within the square bracket, followed by this 3s1. To draw the orbital diagram for sodium, as usual, we have to draw boxes for each and every suborbital, and till 2pz, we have the same pattern as that of neon. The only difference is we have one excess orbital, that is the 3s orbital here. So we need to draw one box for 3s, and one electron is there. So we need to draw one upward arrow mark, which represents the positive spin of the electron. Now let us write the electronic configuration of magnesium, atomic number 12. So it has how many electrons? 12 electrons. To write the electronic configuration, as usual, we have to write 1s2, 2s2, 2p6. Up to this, we have 10 electrons, right? So here we have 12. So 12 minus 10, remaining 2 electrons will be there. Those 2 electrons occupies the 3s orbital. Here also we could see the configuration of neon. Both these pattern for writing electronic configuration is acceptable. To draw the orbital diagram, as we have done for sodium, we have to draw for magnesium also. Starting from 1s orbital up to 2pz orbital, we have the same configuration as that of sodium. But when we come to 3s orbital in magnesium, we have 2 electrons. Here in sodium and magnesium, you could see electrons are added to the next higher shell, that is M shell, right? Since these electrons occupies the next higher principal quantum number, we call these electrons as valence electrons. As I said earlier, the electronic configuration starting from sodium to argon follows exactly the same pattern as that of lithium to neon, right? So students, please pause the video for 2 minutes and try to write the electronic configuration of aluminium, silicon, phosphorus, sulfur, chlorine, and argon. I will display the electronic configuration from aluminium to argon in the next 2 slides. You can check with your electronic configuration. So here in this slide, I have given the electronic configuration of aluminium, silicon, and phosphorus. If you look at the electronic configuration of these 3 atoms, you could see the 3p orbitals are progressively occupied. So in this slide, I have given the electronic configuration of sulfur, chlorine, and argon. So while filling up the electrons in 3p orbitals, that is the degenerate orbitals, you have to remember Hund's rule of maximum multiplicity. In potassium and calcium, the 4s orbital being in the lower energy than the 3d orbital. If you look at the increasing order of energy, we could see the 4s orbital has lower energy than 3d orbital, right? So electrons occupy 4s orbital before it occupying 3d orbital. Now let us see the electronic configuration of potassium with atomic number 19, which means it has how many electrons? 19 electrons. We have to write 1s, 2s, 2p, 3s, 3p. Then you have to write 4s. Instead of 3d, you have to write 4s. Right? Now, coming to the number of electrons. How many electrons we have? 19 electrons. So we need to fill all the 19 electrons in these suborbitals, right? So 1s2, 2s2. When coming to 2p orbital, it could accommodate how many electrons? 6 electrons. Coming to s orbital, again 2. Coming to p orbital, again 6. Now, 2 plus 2 plus 6 plus 2 plus 6. On the whole, we have completed 18 electrons. But in potassium, we have 19 electrons, right? So 19 minus 18, remaining 1 is there. That electron won't occupy the 3d orbitals. Instead, it will occupy which orbital? 4s orbital. Because 4s orbitals are lower in energy than 3d orbitals. No need for you to draw this empty orbitals like this, okay? Now coming to calcium. So according to Hopper principle, we need to write the electronic configuration in the increasing order of energy. So 1s, 2s, 2p, 3s, 3p, then we have to write 4s, right? So 1s2, 2s2, 2p6. Up to this, we have neon configuration, right? Then 3s2, 3p6. So totally how much we have written? 2 plus 2 plus 6 plus 2 plus 6. Totally we have written 18 electrons. On the whole, we have 20 electrons in calcium. So 20 minus 18, remaining how much we have? 2 electrons. These 2 electrons, will it occupy the 3d orbitals? No, it won't occupy any one of the 3d orbital. It will occupy the 4s orbital. How many electrons are there in 4s? 2 electrons. So we need to draw one upward arrow mark and one downward arrow mark to represent the opposite spins present in 4s orbital. Understand? So that's what we have written here in potassium and calcium. The 4s orbital being in the lower energy than 3d orbital is occupied by 1, that is in the case of potassium, 1 electron, and 2 electrons in the case of calcium, 2 electrons respectively. Students, let's recall the topics that we have discussed in this session. We have discussed the electronic configuration of atoms, notations of electronic configuration, and we have discussed how to write the electronic configuration for the first 20 atoms in terms of scientific notation and orbital diagram. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.